Hello everyone. I'll be talking about integrating egocentric localization for more realistic point-goal navigation agents. Impressive progress has been made in training agents to navigate inside photorealistic 3D simulated environments. One of the most fundamental and widely studied of these tasks is point-goal navigation, wherein an agent is spawned in a never-before-seen environment and asked to navigate to target coordinates specified relative to the agent's start position. Recent prior works have proposed end-to-end learning of policies that directly learn to map pixels to actions at every step. At a high level, an LSTM-based policy takes the previous action, visual observations at the current state, the episode goal coordinates as per the PointNav task specification, and the agent's ground truth proposed in the trajectory as input, and it generates a distribution over a discrete action space as its output at every step. Prior work has shown that large-scale RL training of such architectures enables agents to perform PointNav with near-perfect accuracies. However, an important caveat to note here is that this approach assumes perfect localization via an idealized GPS and compass sensor, which we know is impractical to realize in indoor environments in the real world. Moreover, these approaches also assume pristine conditions of noiseless robot actuations. In this work, we lift these assumptions and explore the problem of PointNav under noisy actuations and without oracle localization. Towards that end, we remove the oracle localization input from the agent and replace it with the agent's estimate of its own location in the trajectory. We do that by equipping the agent with a visual odometry module that is responsible for predicting per-step egomotion estimates. Access to such an odometer allows the agent to cumulatively integrate its localization estimates over the course of its trajectory and hence derive a potentially erroneous substitute of the oracle localization supervision. Let's take a closer look at the visual odometry module. Our odometer comprises of a CNN-based visual encoder that's followed by a task-specific regression head. The model takes a pair of visual observations, in our case depth maps as inputs, and regresses to the relative pose change between the two agent states defined by these input observations. To train our odometry model, we require a dataset comprising of visual observation pairs and ground truth egomotion. In order to collect this dataset, we take an agent that can navigate reasonably well, and we use the agent's policy to unroll trajectories from the Gibson train split. Then we randomly sample points from within those trajectories and record the RGBD maps, the action taken by the agent, and the ground truth egomotion regression targets for training our odometer. Following this protocol, we collect a dataset of approximately 72K observation pairs sampled from 8.7K episodes across 72 scenes in the Gibson train split. We train our odometer on this dataset using a smooth L1 regression loss. Once pre-trained, the odometer is kept frozen and used with the agent's policy for navigation. We compare our method against a host of competitive baselines. The no localization baseline tells us how well an agent would perform the task without any localization information whatsoever during training and evaluation. Dead Reckoning derives egomotion estimates via a static lookup table mapping actions to odometry estimates and does not involve any learning for estimating odometry. In contrast, our approach uses an odometer to learn these egomotion estimates. As a benchmark for upper bound performance, we also report numbers for an agent that relies on ground truth localization information, same as prior work. We also compare with a classic robotic navigation pipeline that has modular components for map creation, localizing the agents on the map via SLAM, followed by planning a path towards the goal. We now take a look at some quantitative results. We make the following observations from our experiments in environments with noiseless robot actuations. Having some form of localization, though erroneous, is critical for the success of PointNav. Learning to infer odometry as in our approach performs better than simply memorizing egomotion estimates. Note that in the absence of noise in the agent's actuations, memorization becomes a very strong baseline. Our approach also outperforms classic robotic navigation pipelines that use SLAM for localization. When our agent's policy that is trained on noiseless actuations is transferred to an environment with noise in the transition dynamics, the performance takes a hit. By simply fine-tuning a learned odometry model to adapt to the actuation noise and keeping the underlying policy frozen, we get significant performance improvements. This result is highly significant because our hot swappable navigation policy circumvents the need for billions of frames and hundreds of GPUs to train navigation policies as done by prior work. By additionally fine-tuning the policy to adapt to the estimates of the recalibrated odometer, we get additional improvements. We show some sample navigation trajectories of our proposed agent. The green line shows the shortest path between the agent's spawn location and target. The line in dark blue corresponds to the actual path taken by the agent, and the light blue line represents the agent's predictions of its location. We also submitted a straightforward modification of our proposed approach to the PointNav track of the Habitat Challenge 2020. Our best performing agent was ranked at number 2 on the test standard leaderboard with respect to SPL and success, and number 1 with respect to soft SPL and distance to goal. To know more, please drop by an interactive session on Wednesday, and thank you.